Chemistry is more than just mixing liquids and observing reactions. It's a fascinating realm filled with peculiar discoveries and mind-bending phenomena. In this video, we delve into the curious world of chemistry, uncovering its weirdest facts and quirkiest wonders. From elements that defy our expectations to reactions that challenge our understanding of the universe, join us as we explore the strange and intriguing side of chemistry. Prepare to be amazed by the unexpected twists and turns that this captivating science has to offer. 1. The carbon in peanut butter can be turned into diamonds. Believe it or not, the carbon in peanut butter can indeed be transformed into diamonds, through a process known as diamond synthesis. While it might sound like something out of science fiction, the concept is grounded in real science and chemistry. Diamonds are made up of pure carbon atoms, arranged in a crystalline lattice structure. The carbon atoms bond together in a unique way under intense heat and pressure, which naturally occurs deep within the Earth's mantle over millions of years. However, scientists have discovered methods to replicate these conditions in a laboratory setting, allowing them to produce synthetic diamonds. One such method involves using a high-pressure, high-temperature apparatus. In this process, carbon-containing materials, such as graphite or even peanut butter, are subjected to extreme pressure and temperature conditions, mimicking those found deep within the Earth. Under these conditions, the carbon atoms rearrange themselves into the crystalline structure characteristic of diamonds. The idea of using peanut butter to create diamonds might sound unusual, but it's rooted in the fact that peanut butter contains carbon-based molecules. When subjected to the right conditions, these molecules can undergo the transformation necessary to form diamonds. Of course, turning peanut butter into diamonds is not a practical or efficient means of diamond production. Industrial processes typically use more refined sources of carbon, such as graphite, which can yield larger and higher quality diamonds more reliably. Nevertheless, the ability to synthesize diamonds from unexpected sources like peanut butter showcases the versatility of scientific innovation. 2. Helium is the only element that was discovered in space before being found on Earth. Helium holds a unique position in the periodic table and in the annals of scientific discovery. It is the only element known to have been first identified not on Earth, but in the vast expanse of space. In 1868, French astronomer Jules Janssen and Norman Lockyer independently observed a yellow line in the Sun's spectrum during a total solar eclipse. They correctly identified this line as arising from an unknown element, which Lockyer named helium, from the Greek word for the sun, helios. However, it wasn't until 1895 that helium was discovered on Earth. The Scottish chemist Sir William Ramsay isolated helium from the uranium mineral cleveite, proving that the element existed beyond the Sun's atmosphere. On Earth, helium is often found alongside other noble gases, like neon and argon, in natural gas deposits. Today, helium is used in a variety of applications, from scientific research and cryogenics to party balloons and airships. 3. Glass is neither liquid nor solid. Glass, a material we encounter in our daily lives through windows, bottles, and various other objects, often leaves us wondering about its true nature. Is glass a liquid or a solid? Traditionally, substances are categorized as either solid, liquid, or gas based on their molecular structure and behavior. Solids possess a fixed shape and volume due to strong intermolecular forces that hold their particles in a rigid arrangement. Liquids, on the other hand, flow and take the shape of their container due to weaker intermolecular forces, allowing their particles to move past each other. Gases have highly energetic particles that fill the entire space of their container. Glass, however, defies easy categorization within this framework. It is an amorphous solid, meaning it lacks the ordered crystalline structure characteristic of most solids. Instead, the atoms or molecules in glass are arranged randomly, much like a liquid, but they are frozen in this disordered state. Despite its non-crystalline structure, glass exhibits many properties of solids, such as rigidity and resistance to compression. However, it also shares characteristics with liquids, such as the ability to flow over long periods, albeit extremely slowly. Its non-crystalline structure and ability to flow over time distinguish it from conventional solids, yet its rigidity and resistance to flow at room temperature set it apart from liquids. 4. Hot water freezes faster than cold water. The statement, "hot water freezes faster than cold water," may initially sound counterintuitive, as one might expect that hot water would take longer to freeze than cold water. However, this phenomenon is known as the Mpemba effect, named after a Tanzanian student named Erasto Mpemba who observed it in the 1960s. Several factors contribute to the Mpemba effect, and the exact conditions under which it occurs can vary. One primary factor is the rate of heat loss during the cooling process. Hot water loses heat more rapidly than cold water due to a higher temperature gradient between the hot water and its surroundings. As hot water begins to cool, its molecules move more energetically, and the heat energy is released more quickly into the surrounding environment. On the other hand, cold water has less thermal energy to lose initially, so it may take longer for it to reach the freezing point. Another contributing factor is the formation of ice crystals. In some cases, hot water might start forming ice crystals more quickly than cold water due to factors such as supercooling, where the water temperature drops below its freezing point without actually turning into ice. This can lead to faster ice crystal formation when hot water is rapidly cooled. It's important to note that the Mpemba effect is not universally observed under all conditions, and there are instances where cold water may freeze faster than hot water. The specific outcome depends on various factors, including the initial temperatures of the water, the presence of impurities, and the container used for cooling. 5. Carbon dioxide directly converts from a solid to a gas without melting. Carbon dioxide, a gas commonly associated with climate change and the carbon cycle, has a unique property known as sublimation. Sublimation is the process by which a substance transitions directly from a solid to a gas without going through the intermediate liquid phase. Carbon dioxide is one of the most well-known examples of a substance that undergoes sublimation. When dry ice, or solid carbon dioxide, is exposed to normal atmospheric pressure, it skips the liquid phase and goes directly from a solid to a gas. This process is known as sublimation, and it's a fascinating demonstration of the complex behavior of matter. The reason for this behavior lies in the thermodynamic properties of carbon dioxide. At normal atmospheric pressure, the temperature at which carbon dioxide exists as a liquid is below the freezing point of water. This means that the liquid phase of carbon dioxide is not stable under normal conditions and will quickly sublimate into a gas. Sublimation of carbon dioxide is not only a curious scientific phenomenon but also has practical applications. For example, dry ice is often used in cooling systems because it can quickly and efficiently transition from a solid to a gas, providing a cooling effect without the mess of melting ice. 6. Hydrogen is lighter than air. Hydrogen is indeed lighter than air, making it a fascinating element with unique properties. Its lightness stems from its atomic structure, consisting of a single proton and an electron. This lightness allows hydrogen gas to ascend when released into the atmosphere, just like helium, which is another gas lighter than air. This property of hydrogen has several practical implications. For example, hydrogen-filled balloons will float in the air due to their lower density compared to the surrounding atmosphere. Additionally, hydrogen-filled airships, or dirigibles, can achieve flight by using hydrogen's low density to provide lift. However, the low density of hydrogen also poses some challenges. For example, hydrogen gas can escape from containers more easily than other gases, and it can be difficult to transport and store due to its low density. 7. The element argon is named after the Greek word for lazy. Argon, the noble gas found in the Earth's atmosphere, has an interesting origin story behind its name. The term argon is derived from the ancient Greek word argos, which means lazy or inactive. The name was chosen by the British scientists who first isolated and identified argon in 1894, Lord Rayleigh and Sir William Ramsay. They chose the name argon to reflect the element's chemical inertness, meaning it does not readily react with other elements. The Greek root argos is appropriate for argon because it is known for its lack of reactivity. As a noble gas, argon has a full set of electrons in its outermost energy level, which makes it highly stable and unlikely to participate in chemical reactions. Despite its name, argon plays an important role in many industrial processes and applications. For example, it is often used as an inert atmosphere for welding and other high-temperature processes, where its lack of reactivity helps prevent materials from oxidizing or reacting with other gases. 8. Lithium is used to treat bipolar disorder. Lithium, the soft silver-colored metal, has a fascinating history in the field of medicine. In particular, it has been used for decades as a treatment for bipolar disorder, a mental health condition characterized by episodes of mania and depression. The use of lithium in medicine was first discovered in the late 19th century, when it was found to have a calming effect on patients with psychiatric disorders. However, it wasn't until the late 1940s that its effectiveness in treating bipolar disorder was recognized. Lithium's mechanism of action in treating bipolar disorder is not fully understood, but it is believed to help stabilize mood by regulating the levels of certain neurotransmitters in the brain, such as serotonin and dopamine. In addition to its use in treating bipolar disorder, lithium has also been studied for its potential use in treating other conditions, such as major depressive disorder, schizophrenia, and even Alzheimer's disease. However, more research is needed to fully understand its efficacy and safety in these areas. 9. Ice cubes made with boiling water are transparent. Ice cubes, commonly used to cool down drinks or add a bit of chill to a cocktail, are typically made by freezing water in a tray. However, there is a fascinating way to create ice cubes that are clear and transparent rather than cloudy and opaque, by using boiling water. The process of making clear ice cubes involves boiling the water before freezing it. This might seem counterintuitive, as boiling water is typically associated with hot temperatures rather than the cold of ice. However, there is a scientific explanation behind this method. When water is heated to boiling, it becomes more oxygen deprived. This lack of oxygen reduces the formation of tiny air bubbles that can become trapped in the ice as it freezes. These air bubbles are what give ice cubes their cloudy appearance. By using boiled water, these bubbles are minimized, resulting in clear and transparent ice cubes. This method is often used in professional settings, such as high-end restaurants and bars, where clear ice cubes are valued for their aesthetic appeal and ability to showcase the drinks they accompany. However, making clear ice cubes at home using this method does require some patience and effort. After boiling the water, it must be allowed to cool and then poured carefully into an ice cube tray to minimize any disturbance that could reintroduce air bubbles. The tray is then placed in the freezer, and the ice cubes are left to freeze slowly and evenly. In conclusion, the process of making ice cubes with boiling water results in a unique and visually appealing product. By reducing the formation of air bubbles, clear and transparent ice cubes are created, adding an extra touch of elegance to any drink. 10. Clouds are not purely gas. Clouds, those ethereal formations that grace the skies, are often thought of as mere collections of gas and water vapor suspended in the atmosphere. While it's true that clouds primarily consist of water droplets or ice crystals, they are not purely gas. In fact, clouds are complex and dynamic structures composed of various elements and processes beyond just air and water vapor. At their most fundamental level, clouds form when warm, moist air rises and cools, causing the water vapor within it to condense into tiny droplets or ice crystals. These droplets or crystals then cluster together to form visible clouds. However, the composition of clouds extends beyond water molecules. Clouds often contain suspended particles and aerosols, such as dust, pollen, pollutants, and even microorganisms. These particles serve as nuclei around which water vapor can condense, facilitating cloud formation. In areas with significant air pollution, such as urban environments, these aerosols can heavily influence cloud properties and behavior. Furthermore, clouds interact with and reflect sunlight, playing a crucial role in regulating Earth's climate. They act as both insulators, trapping heat within the atmosphere, and reflectors, bouncing sunlight back into space. The composition and density of clouds affect their ability to absorb or reflect solar radiation, making them integral components of the Earth's energy balance. 11. The word chemistry comes from an ancient Egyptian term. The word chemistry has a long and fascinating history that can be traced back to the ancient civilizations of Egypt and Greece. The roots of the word chemistry can be found in the ancient Egyptian word, chemia, which referred to the process of transforming or transmuting matter. The ancient Egyptians made significant contributions to early chemistry, particularly in the realms of metallurgy, medicine, and embalming practices. The term, chemia, was later adopted by the ancient Greeks, who used the word, chimia, to describe the art of alchemy, which was the forerunner of modern chemistry. Alchemy was the pursuit of transforming base metals into gold and creating elixirs of life and immortality. During the Middle Ages, the term chimia was used by alchemists and early scientists to describe the study of the properties and transformations of matter. Over time, the term evolved into chemistry in various European languages, including English, French, and German. Today, the term chemistry encompasses a vast and diverse realm of scientific exploration, including investigations into atomic structures, properties, and the intricate dynamics of chemical reactions occurring within living organisms. Thanks for watching, and don't forget to hit that like button.